Hello, everyone. My name is Shuo Chen. I'm a researcher of Microsoft Research. This is a joint work with my colleague Shez Kadir of Microsoft, Matt McCutcheon of MIT, Fan Kao, and Ravi Iyer of University of Illinois. So today I'm going to introduce a framework for safer integrations of single sign-on services. So I think most people have the experience of single sign-on or SSO. For example, if you go to Airbnb.com, so when you click sign in, log in, it allows you to use your Facebook or Google identity. So with just one click, Now I'm signed in to Airbnb. Right? This is very convenient for users. It's also very convenient for website administrators who do not need to manage user identity, which would be a big headache. Single sign-on or SSO is really the front door lock for tens of millions of websites. Many companies, provide identity services. So here I show you 30 companies providing such services, but there are more companies. And these companies provide SDKs for different web languages like ASP.NET, PHP, Node.js, many other languages. And they also provide step-by-step instructions to teach developers how to integrate such services and SDKs to their websites. So as a website developer, you are expected to know something about the underlying protocol, this is the OpenID Connect protocol, which is pretty complicated, as you can see here. And also, you are expected to know if you use a specific SDK, you are supposed to know how to use this specific SDK. For example, right now you are seeing this Microsoft Azure Active Directory SDK for Node.js. So you are expected to follow step 1, 2, 3, 4, 5. You need to understand these things and then put this into your website. However,
there's a buzz on your app. Oh, just plug this a second.
Oh.
Carry on, I'm just going to swap these things over. Carry on, I'm going to swap these over.
Oh, okay. Okay. Oh, so, okay. So, should I continue? Is most website programmers are not experienced locksmiths. So imagine that you are asked to put a lock on your front door. So you buy this product from a hardware store, and then you read the installation guide, then you drill holes, you put some a lock cylinder, some plates, and not everybody can do this, right? So similarly, if you expect an average website developer to integrate single sign-on services, the question is whether they are able to do this securely. And it turned out that there are many studies showing that security critical logic bugs are pervasive on websites. So these studies have been published in leading academic security conferences as well as in Black Hat conferences. So last year in Black Hat USA and Black Hat Europe, there were talks about SSO integration problems. And because of these problems, an attacker can sign into a victim's account, or an attacker can stealthily cause the victims to sign into the attacker's account, which is commonly known as login request forgery. And there was a report from the Cloud Security Alliance, which ranked API integration bugs as the #4 cloud security top threat. And SSO logic bugs are the primary example of that bug category. So next, I'm going to show you a few video demos. So the first demo is about Microsoft Azure Active Directory library that we just saw a few minutes ago. So this bug allows the attacker to log into the victim's account. Yeah. In this demo, I'm going to show you a vulnerability that we discovered in the Node.js package of Azure Active Directory. The problem has been fixed. What happened was that if a developer simply follows an earlier version of this developer guide, he will end up having a website like this. And please ignore the certificate error, which is unrelated to this problem. So in this sample website, you can see a link. If the user clicks on this link, then he can log in, and this is the account information. And in particular, this is the preferred username. So it is my identity, shortchen@microsoft.com. So this looks good. However, the problem is actually an attacker can log into your account, and an attacker actually can completely fake the identity information. For example, suppose I want to log into the website as Bill Gates. So I can fill in this form. Name is Bill Gates, and the email is billg@microsoft.com, for example. And I can also copy whatever I want. Then I can directly post this set of identity to the website, and you can see that the website consider this is my name, and even this preferred username can be faked arbitrarily. So the problem, because of this bug, anybody can get into the victim's account because there is an important security check missing in the SDK's developer guide. And the second demo I'm going to show is login request forgery on Skype Online. It caused a victim to
now I'm going to show you the
attacker's account.
login forgery problem. So now suppose this is a victim machine, and the victim received an email. Now I'm going to show you that at this point, the victim has not logged into the account. But if the victim just click on this link, so you can see that the victim has logged into this fake account that I created a moment ago. And in fact, this you can really communicate from the attacker machine. So this is a demo. Okay, then what I'm showing you is now you really get into this fully functional fake account. Hello. Yeah, so it's this kind of request forgery problem is actually pretty common when website implement single sign-on protocol.
So these are just two problems that we discovered in the past few years. We have reported many SSO issues to various companies and relying party websites. So I want to say that even big companies make this kind of mistakes. So let's go a little deeper to understand what are the tricky things when you really adopt a single sign-on. So here I give you an example, which is a bug due to insufficient logic checks using Google ID. And this was back in 2012 when Google ID was based on the OpenID 2.0 protocol. The protocol is fairly complicated, but I'm going to explain a highly simplified version of the protocol. So in this simplified explanation, I have only two browser redirections. So a browser redirection is essentially a message sent from a website to the client. And if the client is an honest browser, the client should forward the message to the destination website. That is called a browser redirection. So in redirection 1, there is a field realm equals the relying party's identity, and then required equals email first name and last name. So essentially the relying party is telling Google ID that please give me the email first name and last name of the user. Okay. So when this redirection is received, then the Google service generate essentially a sealed envelope, and inside the envelope you see email first name and last name, and it also indicates that these three fields are protected by the signature, and there is a signature as the seal. Now, when the redirection 2 comes back to the relying party will validate the signature and then authenticate the user as alice@a.com. Okay, so this seems to be straightforward. However, when we consider in the real scenario, it is a little bit complicated because now let's assume Bob is an attacker. Now what Bob can do is to remove email from redirection 1. So in this situation, from Google's standpoint, it looks as if the relying party was only interested in first name and last name. Okay, so Google will respond with this sealed envelope, which only contains first name and last name. But now Bob just attach another field called email equals alice@a.com. So think of this as a sealed envelope, and on top of that is a yellow sticker, which says alice@a.com. Now the problem is a lot of relying party websites simply use an SDK certified by Google, and in that SDK, there was a method literally called validate message. And what the method does is to check the signature. But in this case, the signature is okay because Bob didn't attempt to tamper with the signature, right? So once the SDK returns okay, then a lot of websites just happily authenticate the user as alice@a.com, which is incorrect. Now, here is another example. It is due to an unintended usage of OAuth 2.0 access token. Several years ago, the Live ID developer guide showed people how to integrate, how to recognize a user in a mobile app. So for example, we develop a mobile app called Full App, and suppose Alice is running Full App. This is how Full App can recognize the user Alice. First, the app calls a Live ID API login with the basic scope. Essentially, this is to tell the service that I'm going to access this user's basic information, public information. Then, of course, the Live ID service needs to issue an access token to the application. And then with this token, the application can call a REST API me in order to get the user's information. Then Full App is able to recognize the user as Alice. Right? This is also pretty straightforward, and there is no problem in this protocol flow. However, many mobile apps have their backend services. So for example, let's consider Full App has a backend service, full.com. Now, in order to authenticate the client into the backend service, a lot of developers simply pass the token from the client to the backend server. And then essentially the first two steps happens on the client side and then pass the token. Then step 3 and 4 happens in the backend side. And this turned out to be a serious problem. It allows any app on Alice device or any relying party that Alice has ever visited to sign into Full.com as Alice. Essentially, if Full.com is a bank, then even some arbitrary apps like Angry Birds or Pokemon Go is able to get into the bank account. Right? So this is due to a confusion about authentication and authorization. Now, let me use this analogy to explain the root cause of the confusion. Right? So imagine that we have an ID office, and the president authorizes everybody to see his public photo, which is okay because it's just a public photo. Now there is a yellow face here who says, I want to see the photo. Then of course the ID office has to issue the token because everybody should be able to see the photo. Once the access token is obtained, now this yellow face just passes the token to the relying party. Then the relying party presents the token back to the ID office. Then of course, the relying party will get the public photo. So if you think about this whole scenario as authorization, there's really no problem because everybody having the token should see the photo. Right? Now, the real problem is if the relying party concludes that, that's why the yellow face was the president, then he is making a authentication conclusion which does not have any logical base. Right? So it's pretty tricky. So let me show you a vulnerable application because of this confusion. So this application is called Saluto. It has a mobile app and a backend, saluto.com. What we are seeing right now is the victim machine. Then this victim Alice just run any application and turn out to be a malicious application. Oh, let me roll back a little bit. So once she runs the malicious application, the application is able to get the access token. There's no problem because everybody can get the access token. Now this token is sent to the attacker machine, which is this machine. Now when the attacker get the access token, it can directly post the access token to the authentication endpoint of saluto.com. And as a result, you see that this attacker can sign in as Alice, although the only thing the attacker is able to obtain is a almost public access token, which everybody can get. Now, I just show a few demos and explain some of the problems that people can get wrong. And in the rest part of the talk, I'm going to introduce our solution to the problem. It is based on a technology, a program verification technology called self-verifying execution, or SVX. So I think perhaps some of you have heard of the term program verification, but many people may think that program verification is something very automatic. It's like a black box. If you have the source code of a program you want to check, as well as a safety property, and then you can just let this robot to find bugs for you. That would be wonderful, right? It's just have the source code and all the bugs will be found. That would be good. But in reality, program verification is a very challenging task for a number of reasons. The first reason is that the source code alone is not enough. You need to model the runtime platform, like the web server behavior, the operating system, these kind of details. And that is very difficult to be precise. And second, you also need to model the hypothetical attacker, which is able to do all kinds of things. Then essentially, you need to know everything that the attacker is able to do. That it is very difficult to be exhaustive in the modeling. Now, even after the modeling, the theorem is also very difficult. Essentially, what you are going to prove is that if the attacker A is able to call program P for infinitely many times, so there is an infinite loop in your theorem, and every time there are multiple public APIs, then can this safety property fee be violated? So this kind of proof, because of the exponential and infinite possibilities of executions, you need to do inductive proof, which means you expect the developer to come up with something called a loop invariant and some good lemmas in order for the proof to go through. So this is very difficult to automate. Now the purpose of SVX is to lower these hurdles so that program verification can be used to check the real programs, at least in web protocol. The basic idea is that every actual execution is responsible for collecting its own executed code and proving that it satisfies the safety property fee. So in SVX, there's no need to model the attacker because every execution is driven by a real user. There is no need to model the runtime platform because every execution happens at the actual runtime. And also very importantly, there is no need for inductive proof because it only proves that this execution satisfies the property as opposed to a much more difficult theorem, which is all possible executions satisfy the property. Now, I know that this sounds very abstract to you. Let me give you a simple toy example. Imagine that we are building this system, which consists of Alice.com, Bob.com, and Charlie.com. Each has an integer 10, 40, and 5. And each has a public method. Method grab is to simply return Alice value. Method compare is to compare Bob's value with the value in the incoming message, and then return a greater one. Method finish is to compare Charlie's value with the value in the incoming message, and then pick a greater one in M2, and then call conclude M2. Now, as always, we assume the client to be completely untrusted, which can arbitrarily invoke these methods. Now, our safety property is that whenever conclude M2 is reached, M2 must represent the website holding the greatest integer. So essentially, what we are trying to do here is to choose the greatest integer constant among the 3 websites. That's the system we are building. Now, perhaps you expected this kind of execution. First, the client will call grab to get Alice information, to get Alice value, and then call compare to compare Alice value with Bob's value, and then eventually call finish to get the greatest integer of the 3. And in this case, if this is the execution, indeed we get 40 Bob, which is correct because 40 is the greatest integer here. So this is correct. But the system is actually vulnerable because the client can call grab and directly call finish. In this case, the result will be 10 Alice, which is incorrect. So traditionally, if you do program verification, you need to model the website behavior as well as the all possible executions of the client, and then you need to do the inductive proof. If you do everything correctly, then at some point you will be stuck because the theorem is invalid. Once you stuck somewhere, you figure out that there is a possibility of a violation, and this is the attack. And as I said, in reality, this is very complicated. And SVX is quite different. It is simpler. All it needs is a message field called SymT, or symbolic transaction, on every message. So again, let's see the expected execution, the same execution. But notice that in every message, we have this additional field. Initially, this additional field, SymT, is empty. And after grab is called, the SymT becomes alice.com : pound grab. And this execution continues until in the end, this is the result, 40 Bob and this final SymT. The final SymT indicate how we get to the result 40 Bob. It is through grab, compare, and finish. Now, pound grab, pound compare, and pound finish are a compact representation of the executed code of this method. So I'm not giving you the detail of the representation, but let's assume that there is a way to represent the executed code. Now, at this point, whether this execution is secure, it's easy to check. Charlie's conclude method simply calls a program verifier to prove that the final SymT implies the property that we want to ensure. So, for example, in the normal execution, if the code goes through grab, compare, and finish, then indeed this sequence of logic is sufficient to imply the safety property. So the execution is accepted. On the other hand, if the code sequence only consists of grab and directly finish, then the corresponding logic is insufficient to prove this theorem. Then the execution is rejected. And note that in SVX, the program verification is symbolic, which is only about the code, but no concrete data. So that means you can think of as SVX as a middle ground between the traditional offline symbolic verification versus the runtime concrete checking, because SVX is doing symbolic verification, but at the actual runtime, the concrete runtime. And an advantage of SVX is that the performance overhead is near zero, because all the theorems are symbolic and they are cacheable. So that means all normal executions should simply hit the cache and return immediately. There is no noticeable performance overhead. So let me give a little bit detail about this point. So we want Charlie to prove this theorem, SymT implies the property. Now, Charlie has a theorem cache. If the theorem has been proven before, then the result is returned immediately. There is no performance overhead. However, if the theorem has not been proven, then it is given to a verification server on the cloud, which will first recover the code of the execute method and synthesizes a straight line program using the SymT. The synthesized program is given to a program verifier, which will either validate or find a counter example of the execution, and then the verification result is written back to the theorem cache. So if you take this path, it will take like 30 to 50 seconds, which is very expensive. But because of the theorem cache, all normal executions should just hit the cache and return immediately, unless there is a clever attacker who figures out an execution sequence which nobody has seen before. Then it will trigger the long pass. Now, I just explained the basic idea of SVX with a toy example, which had nothing to do with our motivation, single sign-on protocol. Now, next, I'm going to talk about our open source project, SVOS, which is safer SSO integration solutions based on SVX. SVOS is essentially an object-oriented framework with SVX built in. So it has 4 levels. At the top level, which is the protocol independent level, we defined very basic classes like identity provider, relying party, as well as the 2 safety properties, login safety and login intent, which corresponded to the 2 video demos that I showed in the beginning. Login safety prevent an attacker to log into the victim's account, and login intent prevent the victim to accidentally log into the attacker's account. So we defined both properties. Now, then based on the protocol independent level, we derive classes for the protocol level. We have OAuth 2.0, OpenID 2.0, and OpenID Connect. Then further, we derive SDK level classes covering these identity providers. And potentially, every website can further derive classes to build their specific authentication logic. So the advantage of the framework is that every concrete implementation at the most concrete level is guaranteed to satisfy the property that we defined at the top level. So this turned out to be a significant capability because several decades ago, the OO community wanted to achieve a similar goal. So perhaps some of you know about this notion called the Liskov substitution principle, LSP. The principle tried to ensure that if a property is true for the base class, then it holds for all derived classes. So if that was true in reality, then that would be a beautiful thing. You just define the property and then you derive all the classes conform to the property. That would be beautiful. But people soon realize that even some very realistic scenarios have to violate RSP. So this is the most canonical counterexample of RSP. So suppose there is a base class called rectangle. It has width and height, and also it has getters and setters for width and height. So for this base class, you can prove a property which is essentially that the width is independent of the height. And this is true for the base class rectangle. However, several years later, somebody may derive a class called a square. And for his purpose, he has to override the setters in order to keep the shape a square. But once he does that, this derived class will violate the property of the base class that people have already proven before. Right? In SVX, we don't have this dilemma because the verification happens at the actual runtime. There's no confusion due to abstraction. So, for example, if rectangle R is constructed at runtime as a rectangle, then of course we are able to prove that the width is independent of the height. On the other hand, if the rectangle R is constructed at runtime as a square, then we are able to prove that this property does not hold. So there is no confusion because we define the property at the base class, but we actually verify the property at the actual runtime. Okay. So adopting SVX on your website is extremely simple. SVX consists of an agent and an adapter. The agent can be a public, organizational, or local host agent. I skipped the detail here, but the information is in the README file of our project. Now, as a developer, you only need to pick an agent and set its endpoint in the SVOS configuration file, and then copy the adapter folder to your website. That is how you adopt SVOS. Then, assuming you are building a website through.com in PHP and you want to do Facebook single sign-on, the only thing you need to do is to redirect the browser to this URL, which contains foo.com, PHP, and the provider equals Facebook. That's all you need to know. Just redirect. Then magically, the user's identity information will be available in the following session variables. So currently, we give you the user ID, full name, email, and authority. So really, you don't need to know anything about the single sign-on. Just do the redirection, pick up the session variables. So we have covered 7 single sign-on providers: Facebook and Microsoft account, Microsoft Azure, Google, Yahoo, LinkedIn, and Weibo. Also, we support currently. We support 3 languages, but it's pretty easy to support more services and more languages. And we have tried to integrate SVRs with real-world applications. For example, we did integration with MediaWiki. So this is a MediaWiki website, and when I click here, I'm using SVRs, so you can see that the integration is seamless. It took only 8 lines of code changes to do the integration. And this is hot CRP, which is a conference management system widely used in the academic community. So we did this integration. So again, you see that it's in this case, it only took 21 lines of code changes. And also we did integration with CMT, which is another conference management system developed by Microsoft Research. So the project is open source under the MIT license, available on GitHub. This is the project repository. So now finally, I want to show you a demo of SVOS. So first, let's start with, so this is our Facebook class. And for the demo purpose, so this line is actually an important security check. So for demo purpose, I comment out this line. So now the program is buggy. Now we can run this program. So after a while, the server will start. Okay, ignore this part. Okay, so oh, by the way, for this demo purpose, I'm running the local host agent. So both the browser and the agent are running on this laptop. So when I click Facebook login, you can see that the verification starts. So first, the verification server will synthesize the program corresponding to the execution, the final CMT, and then it will compile this C# code into .NET code. Then it will translate the .NET code to a formal language called Boogie, and then prove the correctness of the Boogie code. So right now we are in the stage of proving the Boogie program, and it will take a few, maybe 30 seconds. Okay, so this says there is a counterexample found by the theorem prover. So this gives you the execution trace, so you can step through this counterexample, and then you can figure out why this proof didn't go through. Then so I realized, oh, it's because of missing this important check. But then I fix this bug. We can run the program again. Oh, by the way, because of the proof failure, the transaction, the execution is rejected. Now in the new execution, so again I click Facebook login. So the same process is now compiling the CMT into a program. So now, again, we are doing the theorem proving. Okay, so the proof is done. So you can see that the agent is now accepting this execution, and for the client, you can see that you are logged in. But as you can see that theorem proving is very expensive, right? Now, the cool thing about SVX is that once a theorem is proven, it's only about the code. Once it is proven, it is cached. So from now on, from any browser, anywhere, if you do the same execution, you get it immediately. There is no proof because of the theorem caching. So that's about it. Let me go to, yeah. So here are the takeaway points. First, most website programmers are not experienced locksmiths. So SSO security bugs are pervasive, and even big companies make mistakes. And in fact, this problem is very well known now in the security community. Then I talk about self-verifying execution. It is essentially a locksmith built into a lock product. And this locksmith watches how a lock is opened every time and checks whether it is logically sound. Then I also talk about our open source project SVOS, which is a framework based on SVX for SSO integration. And so please help us by adopting SVOS on your website, or by joining the project to improve the code. We do believe that we are heading toward a promising direction, which will fundamentally address the SSO security bugs. So that's my talk. Thank you very much. And I'm happy to take questions.
Hi, it's a question about the first part of your talk. If I'm correct, in OpenID Connect, each application, its client application accessing the user data is issued normally a client ID and a client secret. It has to be registered on the authentication server. So how could you access the user data with another app if this app was not issued a proper secret and token to access the user data?
Okay. Which one?
It's at the beginning.
Which?
Yeah.
Is this one?
No, I think it's the one with
this one
with the present picture. Like, yeah, this
one.
Where is at one moment you mentioned that basically any application could use the user token, and like Angry Bird or
oh yeah. Okay, so it is this one.
Yeah.
Right. Okay. So the OAuth protocol has two kinds of tokens. This one is called the access token. The other one is called authorization code. So I think what you mentioned is authorization code, which, according to the protocol, is tied to the app ID, the application ID. So this is actually a very good question, because the correct way to implement this scenario is to use the authorization code, which tie to the application ID. But once this kind of access token is like a more powerful thing. Once you get the access token, it's called a bearer token. You can get the information. So that's. Did I answer your question, or maybe I can explain a little bit offline?
Because we've been using that quite a lot. We're working with Keycloak server, so it's an OpenID Connect server, and so we also face quite a few issues with developers. So.
Okay. Yeah.
Thank you.
Hi, you didn't talk much about the self-verification, verifying execution, but I was wondering, doesn't the symbolic transaction suffer from the same problems like forgery and stuff? How do you ensure the integrity of the symbolic token?
Oh, so if I answer your question correctly, if I understand your
Alice could just
correctly,
make a fake symbolic token, right? That claims that she followed the right execution path for your program.
Oh, okay. So, yeah. Also, this is a very, very good question. So, because of the time, I didn't talk about that part. So, what you are asking is, what if these participants try to lie about symbolic transaction, right?
Yeah.
I didn't cover that part, but I can refer you to our paper. We have published a series of papers. So that is taken care of, although I didn't talk about. But I can show you a little bit of this. I talk about this compact representation. Actually, I told you that I was not going to talk about compact representation. In this representation, we have the ability to show whether a message is signed or not, whether a message is a browser redirection or direct server-to-server call. So this kind of things is also baked into the reasoning. So the short answer is we can prevent that. Yeah, thank you.
So in your example, you showed the code working in kind of enforcement mode where you actually disable the actual login. Does the framework give us the ability to enable it in kind of a logging mode where the OAuth will actually complete normally, but then it will log that this should not have been gone through normally? Like kind of to enable the OAuth, like to use it for detection more than kind of enforcement. Is that possible?
Oh, I'm sorry. I missed the first part of the.
So the framework, the SVX auth framework, in the demo you showed us, basically it kind of stopped the actual OAuth flow.
Oh, yeah.
Okay. So
yes.
Is it possible to enable it only logging mode?
Yeah. That is also possible. And perhaps yet another way to do that is we just prove all the theorem up front and then just populate the cache to deploy the cache only. So anything missing the cache will be flagged as a potential attack. So thank you.
Hi. So as I understood, this framework will be for relying parties only and for the 7 ID providers you mentioned. Are you considering extending it for providers and relying parties and with categories of authentication and authorization protocols? Because I was quite busy with this subject this year, and I found out that many big firms are starting to build their own ID providers, and I was facing exactly the same problems you mentioned in this talk.
Yeah. Okay. I'm happy that you bring up this point. So right now, as you said, we only do this on the relying party. So what we do for the proof is that we build those identity provider classes to simulate their behaviors.
Yes.
So that is not ideal. So ideally, we should convince the identity providers to get on board. So Actually, we really look forward to having the SVRs adopted by some early adopters, and then we can kind of snowball this whole thing, and then eventually get big companies on board. That would be wonderful.
Okay,
Yeah.
maybe we can talk.
Yeah. Yeah. Okay. Thank you.
Could you explain a bit more about where the theorems come from? Are they inherent in the framework, or is it up to the developers to populate? How much work does the developer have to do to populate the theorems?
Oh, the theorems is essentially when we execute, we keep track of this SIMT, and eventually when the execution get to the end, the theorem is this: the final SIMT implies the safety property, and currently our safety property, we have two safety properties. One is logging safety, which prevent the attacker to sign into the victim account, and logging intent, which prevent the victim to sign into the attacker's account. So I think my answer to your question is yes. The theorem is generated automatically because final SIMT is automatic, and the properties are predefined.
Which party most naturally owns the theorem proving engine or implementation of theorem proving?
The relying party. Yeah, thank you very much.